What if the deadliest threat inside a mine wasn't the explosive gas, the collapsing walls, or the depth itself, but a machine everyone walked past every single day without a second thought? Before the fire, before the screams, before the smoke swallowed entire tunnels, the conveyor belt was just there, moving endlessly, humming in the background like it always had. No alarms, no red flags, no sense of danger. And that's exactly why it became a death sentence. Conveyor belts are the veins of underground mining. They move coal or debris hour after hour, shift after shift, so familiar that workers stop seeing them. They fade into the environment, becoming part of the mine's normal. On the day this disaster began, the belt was running under full load, carrying material through narrow passages where heat, dust, and friction quietly accumulated. Nothing looked wrong, nothing sounded urgent, and that false calm would cost 121 lives. The fire didn't start with an explosion. It didn't announce itself with a dramatic failure. It started invisibly, at a single point where metal met rubber, where misalignment caused friction just slightly above tolerance. That friction produced heat. The heat met coal dust, and the dust, dry, fine, and suspended in the air, became fuel. All of this happened while the belt continued to move, feeding the fire forward like a fuse burning into the heart of the mine. What makes this moment terrifying is not how rare it was, but how predictable it should have been. Conveyor belts generate heat by design. Bearings wear down, rollers seize, dust settles everywhere. Every safety manual acknowledges these risks, yet inspections are often rushed, visual, or postponed. Components hidden beneath guards or behind panels become tomorrow's problem. In this mine, the belt section that failed hadn't been physically inspected in months. On paper, everything was compliant. In reality, the system was quietly preparing to ignite. As smoke began to form along the belt line, it traveled faster than any human could run. Conveyor tunnels act like wind channels underground, pulling oxygen through narrow spaces and pushing toxic gases deeper into the mine. Within minutes, visibility dropped to zero. Carbon monoxide levels spiked. Workers farther inside had no idea what was happening, only that the air suddenly burned their lungs and the lights ahead vanished into darkness. Some miners tried to follow evacuation routes they had memorized during training. Others hesitated, unsure if this was a drill, a temporary malfunction, or something worse. The delay was fatal. Fires in mines don't behave like surface fires. They move low, fast, and silently. By the time alarms sounded, the conveyor belt, the same machine no one had inspected, had already turned the mine into a trap. This wasn't a freak accident. It was the result of accumulated neglect, normalized risk, and a system that assumed no news meant no danger. The belt didn't fail. Dramatically, it did exactly what neglected systems always do. It waited until the worst possible moment to reveal the truth. And the most haunting part is this: if someone had stopped, just once, to question what everyone else ignored, the fire never would have started. The mine would have gone quiet at the end of the shift, and 121 people would have gone home. If this story is already making you uncomfortable, that's not by accident. These disasters only make sense when we slow down and truly understand how they happen. Take a moment to leave a comment sharing what you think was the biggest failure so far. Was it the inspection process, the design of the system, or the culture of ignoring normal risks? Your perspective matters here. And if you want more deep, investigative stories that expose how small industrial failures turn into massive tragedies, make sure to hit the like button and subscribe to the channel so you don't miss what comes next. Conveyor belts exist in a strange category inside heavy industry. They are everywhere, essential to production, constantly moving, yet almost never treated as threats. In mines, they are considered infrastructure rather than machines, something closer to a wall or a tunnel than an active system capable of killing. That perception is where the danger begins, because when a system becomes invisible, it stops being questioned. From an engineering standpoint, conveyor belts are complex assemblies under continuous stress. Motors pull tons of material across kilometers of rollers. Bearings rotate thousands of times per hour. Rubber surfaces flex, heat, and degrade. Every one of those components has a failure mode, and many of them fail slowly, quietly, without dramatic warning. But inside most mines, these belts are classified as low risk compared to explosives, gas pockets, or structural collapse. That classification shapes everything that follows. Maintenance priorities reflect perceived danger. High-risk systems receive frequent shutdowns, physical inspections, sensor redundancy, and strict sign-off procedures. Conveyor belts, by contrast, are often checked visually while running. Guards stay in place. Covers remain closed. If the belt is moving and production is uninterrupted, it is assumed to be safe. In many operations, stopping a conveyor for inspection is viewed as a last resort because it halts the entire mine. This mindset creates blind zones. Rollers hidden beneath the belt are rarely touched by human hands. Heat buildup inside sealed housings goes unnoticed. Dust accumulates in layers thick enough to ignite, yet thin enough to look harmless. Over time, small deviations become normal. A slightly higher operating temperature, a faint burning smell during peak load, a vibration that wasn't there last year. Each one is logged mentally as how things are now. Safety systems don't fail all at once, they erode. And conveyor belts are especially vulnerable to this erosion because they sit at the intersection of mechanical wear and human complacency. Workers walk past them every shift. Supervisors hear them every day. Engineers see the same readings week after week. Familiarity replaces curiosity. In the mine where 121 people would later die, the conveyor belt that ignited had been modified multiple times over its operational life. Load capacity had increased. Speed had been adjusted to meet production targets. Replacement rollers came from different suppliers over the years. None of these changes were individually dangerous. Together, they altered heat profiles and friction patterns in ways no original risk assessment accounted for. But risk assessments are rarely revisited unless something goes wrong. That is another structural flaw. Once a system is labeled low risk, it tends to stay that way on paper, even as reality changes. Documentation ages, assumptions harden, the belt keeps moving. What makes conveyor belts uniquely dangerous in mines is not just that they can catch fire, it's how they behave when they do. They stretch through long, narrow tunnels, effectively connecting every section of the mine. When fire starts on a belt, it doesn't stay localized. It travels along the same path workers rely on for transport and escape. Smoke follows airflow. Heat follows material. The very system designed to move resources efficiently becomes a delivery mechanism for disaster. Yet because belts are seen as passive, their role in emergency scenarios is often underestimated. Training focuses on explosions and collapses, not on fires creeping silently through beltways. Workers are taught to fear sudden events, not slow-burning ones. That mismatch between training and reality costs time, and in a mine, time is measured in breaths. By the time anyone realizes the belt is the problem, the system has already done its damage. Not because it was malicious, not because it was poorly designed, but because it was never truly seen. If you've ever worked around industrial systems like this, you've likely seen similar blind spots. What part of this feels most familiar to you? The normalization of small warning signs, or the pressure to keep production moving? Leave a comment sharing your thoughts. The most dangerous part of this disaster didn't arrive suddenly. It accumulated, layer by layer, shift by shift, day after day. Long before flames appeared, the mine was already primed to burn, and almost no one understood how close it was to ignition. Coal dust is an unavoidable byproduct of mining. Every cut, every transfer point, every moving belt releases microscopic particles into the air. Some settle on surfaces, others remain suspended, invisible, drifting through tunnels with airflow patterns that few workers ever see or question. On conveyor systems, this dust behaves differently. The belt's motion constantly disturbs settled particles, lifting them back into the air, redistributing them along rollers, frames, and enclosed housings. Over time, dust builds up in places inspections rarely reach. Under guards, inside roller assemblies, along friction points where rubber meets metal. These areas don't look dramatic. They don't leak. They don't spark. They simply sit there, waiting for one variable to change. Heat is that variable. Conveyor belts generate heat by default, but normally it dissipates safely. The problem begins when friction increases beyond design limits. A seized roller, a misaligned belt, a bearing beginning to fail. Each one adds just a few degrees of temperature. Not enough to trigger alarms, not enough to stop production, but enough to dry surrounding dust into a highly combustible layer. What makes this process so lethal is how slow it feels. Operators don't see flames, they don't feel danger, they feel continuity. The belt still moves, material still flows, production targets are still met, and so the system is allowed to keep heating itself, quietly converting dust into fuel. In the mine where 121 workers would later die, investigators would eventually determine that dust accumulation along the conveyor had reached critical density weeks before the fire, but no one measured it. No one tested ignition thresholds. No one stopped the belt long enough to physically inspect beneath it. Visual checks from a distance showed nothing unusual. On paper, everything remained within acceptable limits. Then friction crossed a line no one was watching. At a single point along the belt, heat concentrated, the rubber surface degraded, dust began to smolder, not burn smolder. That distinction matters. Smoldering fires don't announce themselves with flames or noise. They produce heat and toxic gases first. Carbon monoxide begins to rise. Oxygen levels drop. By the time visible smoke appears, the environment has already become hostile to human survival. Once ignition occurred, the conveyor belt acted like a continuous wick. Fire didn't spread randomly. It followed the belt's path, consuming dust deposits along the way. Airflow fed it. Movement sustained it. The system that had quietly transported material now transported destruction. This is where many assumptions fail. People imagine fires as sudden events. In reality, industrial fires often begin as chemical processes, invisible and gradual. They grow inside systems designed to hide their own vulnerabilities. And because nothing appears wrong until it's too late, response windows shrink to minutes or seconds. Workers deeper in the mine had no way to know that the conveyor had become an ignition source. There were no localized alarms for belt overheating, no real-time dust concentration monitoring, no automatic shutdown triggered by friction anomalies. The system relied on human observation, but humans were trained to look elsewhere. By the time smoke reached occupied areas, the fire had already traveled far beyond its origin point. Escape routes intersected beltways, ventilation systems redistributed toxic gases, disorientation set in, and the invisible chain reaction that started with dust and friction became unstoppable. This is the most uncomfortable truth of all. Nothing went wrong in the dramatic sense. Everything worked as it had been allowed to work. The danger wasn't created by one failure, but by many small tolerances stacking silently until physics took over. On paper, this mine looked safe. Inspection logs were complete. Maintenance reports were signed. Safety audits showed compliance. Every checkbox that mattered to regulators had been marked, every form filed on time. And yet, the conveyor belt that would eventually ignite was slowly deteriorating in plain sight. The gap between documentation and reality was not subtle, it was systemic. Industrial safety programs are built around procedures, but procedures only work when they reflect what actually happens on the ground. In many heavy industries, inspections evolve into rituals rather than investigations. A supervisor walks the route. A technician listens for unusual sounds. A checklist is reviewed. If nothing appears visibly broken and production is uninterrupted, the system passes. What these inspections rarely capture are conditions that exist beneath guards, inside sealed housings, or at friction points that can only be evaluated when equipment is shut down. In this mine, conveyor inspections were largely non-invasive. Stopping the belt required halting production across multiple sections, triggering delays, financial losses, and management scrutiny. Over time, that pressure shaped behavior. Inspectors learned what could be checked quickly and what was better left alone. Components that required disassembly became low priority. Heat measurements were taken at accessible points, not at known friction zones. Dust levels were noted generally, not quantified. This is how compliance becomes misleading. A system can meet every written requirement while drifting further from actual safety. The conveyor belt passed inspections because the inspections were not designed to catch the type of failure that occurred. No one violated procedure. They followed it faithfully. There is also a psychological element that rarely appears in reports. Repetition dulls suspicion. When the same machine runs day after day without incident, it creates confidence, even when conditions subtly change. Inspectors begin to trust the system rather than question it. An unusual smell becomes just the belt warming up. A vibration becomes normal where each inspection reinforces the belief that nothing is wrong, because nothing has gone wrong yet. Investigators later discovered that the conveyor section where the fire started had not been physically accessed during inspections for a long time. Guards remained bolted in place. Rollers beneath the belt were never spun by hand. Bearings were assumed functional because the belt continued to move. The system was judged by output, not by internal condition. What makes this particularly dangerous is that paperwork creates a false sense of security, not just for operators, but for decision makers. Management reviews, reports, sees compliance, and concludes risk is under control. Budgets are allocated elsewhere. Training focuses on more visible hazards. Over time, the idea that the conveyor could be a critical ignition source simply disappears from risk discussions altogether. In this case, the inspection process didn't fail because it was ignored, it failed because it was trusted too much. The forms were accurate reflections of the inspection process, but the inspection process itself was insufficient. That distinction matters. It means no single person can be blamed for skipping a step. The entire system was structured to miss the problem. This is a recurring pattern in industrial disasters. The danger isn't hidden because people are careless. It's hidden because systems reward continuity and punish interruption. Stopping a belt for deeper inspection feels like overreacting until the day it doesn't. When the fire finally forced a shutdown, it was the first time in months that anyone truly saw the condition of the belt from the inside. By then, it no longer mattered. Long before flames appeared, the mine was already speaking. The problem was that no one was listening in the right way. The warning signs were there, scattered across days and shifts, subtle enough to be dismissed, familiar enough to feel harmless. And that is how they survived long enough to become deadly. Workers later recalled small changes that, at the time, didn't feel urgent. A conveyor that sounded rougher during peak load. A faint burning odor that appeared briefly and vanished. Occasional delays where materials seemed to hesitate on the belt before moving again. None of these stopped production. None triggered alarms. Each one was absorbed into the background noise of industrial work. This is how normalization works. When a system operates under stress every day, minor deviations become expected. People stop asking why something changed and start adjusting their expectations to match it. A smell becomes part of the process. A vibration becomes old equipment. The human brain is exceptionally good at adapting to danger, when that danger does not immediately punish it. In this mine, the conveyor belt had been running hotter than usual during certain shifts. Load levels fluctuated as production targets increased, pushing the system closer to its thermal limits. Sensors, where they existed, were placed at generalized points, not at the exact friction zones where failure would begin. Operators monitored averages, not spikes. Short bursts of abnormal heat disappeared into data trends. There were also behavioral signals. Maintenance crews began scheduling minor adjustments more frequently, tightening here, lubricating there, without ever stopping the belt completely. These interventions reduced symptoms temporarily, but masked the underlying problem. Each fix reinforced the belief that the system was under control. This is one of the most dangerous phases in any industrial failure. The phase where a system is no longer healthy, but still functional. It creates confidence precisely when caution is needed most. The conveyor had not failed, so it was assumed it would not fail. That assumption shaped every decision that followed. Communication breakdowns made things worse. Workers who noticed unusual conditions had no clear pathway to escalate concerns unless something was visibly broken. Reporting something feels off carried social and professional risk. No one wants to be the person who stops production over a smell that might disappear by the next shift. Over time, silence becomes the safer choice. Investigators would later reconstruct timelines showing that multiple people, across different shifts, had independently noticed signs of abnormal operation. None of those observations were connected. No single report triggered a response. Each warning existed in isolation, stripped of context, dismissed as coincidence. This fragmentation is critical. Industrial disasters rarely result from one ignored alarm. They result from many weak signals failing to combine into a clear picture. When systems are complex, danger announces itself indirectly. If organizations only respond to obvious failures, they guarantee that the first clear signal will also be the last. By the time smoke was finally visible, the mine had already passed the point of recovery. The early warnings had come and gone, absorbed by routine, smoothed over by experience. and neutralized by the belief that we've seen this before. That belief is powerful. It keeps operations running. It keeps people calm. And in moments like this, it quietly removes the last chance to intervene. If you've ever caught yourself ignoring a small irregularity because nothing bad happened last time, you've felt this pressure. What early warning do you think industries are most likely to dismiss, and why? The fire began where no one was looking. In a section of the mine most people passed without slowing their pace. There was no explosion, no sudden collapse, no dramatic moment that forced attention. The first stage was almost gentle, a slow rise in temperature at a single friction point, rubber softening, dust darkening, oxygen feeding a reaction that did not yet look like a fire. Inside conveyor systems, this is the most dangerous moment. Smoldering does not behave like open flame. It hides. It produces heat and toxic gases before light or smoke ever become visible. Carbon monoxide begins to spread through airflow routes long before anyone smells burning material. By the time smoke detectors react, the environment is already hostile to human survival. As the conveyor continued to move, it did exactly what it was designed to do. It transported material forward. But now it was also transporting heat, embers, and ignition potential along its entire length. Every dust deposit became fuel. Every roller became a possible secondary ignition point. Instead of one localized fire, the mine was suddenly dealing with a moving source of combustion threading through its tunnels. The structure of the mine amplified the danger. Conveyor routes often intersect with ventilation corridors, escape paths, and work areas. Airflow designed to remove dust and gases now fed oxygen directly into the fire. The same currents that kept miners breathing under normal conditions began distributing smoke and carbon monoxide deeper into occupied sections. Workers closest to the ignition point never saw flames. They felt heat first. Then came the irritation in the throat, the pressure in the chest, the sudden difficulty breathing. Vision blurred as smoke thickened. Disorientation set in quickly. In underground environments, even experienced workers can lose their sense of direction within seconds once visibility drops. Farther inside the mine, people noticed something different. Lights dimmed as power systems reacted to heat damage. Communication systems began to fail intermittently. Some assumed it was a routine electrical issue. Others hesitated, unsure whether evacuation protocols applied. In mines, false alarms are common enough to breed doubt. That doubt costs time. By the time the conveyor belt fire was fully recognized as the source, it had already traveled beyond the original zone. Fire suppression. Systems designed for localized equipment failures were ineffective against a moving ignition line. Stopping the belt now meant stopping it while it was already burning, trapping fire in enclosed spaces filled with fuel. Attempts to shut down sections of the system came too late. Heat had compromised structural components. Smoke filled primary escape routes. In some tunnels, temperatures rose rapidly, making passage physically impossible. What began as a maintenance failure was now an environmental catastrophe unfolding underground. This is the moment where control is lost. Once fire integrates with airflow, movement systems, and human pathways, it stops behaving like a mechanical problem and starts behaving like a living force. It adapts to the environment, exploits design features, and accelerates through spaces never meant to contain it. The most terrifying aspect is how quickly this transition happens. From the first ignition to widespread smoke infiltration, the window for effective response was measured in minutes. By the time alarms sounded clearly enough to remove doubt, many workers were already moving through contaminated air without realizing how severe the danger had become. And still, at this stage, not everyone understood what was happening. Some believed the fire was contained, others assumed evacuation routes remained clear. The conveyor belt, invisible in the smoke, had already rewritten the rules of survival inside the mine. What failed next was not machinery, but coordination. When the fire began spreading through the conveyor system, the mine still had one remaining line of defense: its emergency response. Alarms, communication protocols, evacuation routes, trained decision-making under pressure. On paper, all of it existed. In practice, it unraveled almost immediately. The first problem was clarity. Initial alarms were inconsistent, activating in some sections while remaining silent in others. In underground environments, this creates confusion rather than urgency. Workers are trained to verify before reacting. because unnecessary evacuations are disruptive and frequent false alerts condition people to wait for confirmation. In those early minutes, many miners hesitated, trying to understand whether this was a localized issue or a full-scale emergency. Communication systems did not help. As heat and smoke spread along conveyor corridors, cables and relay points began to fail. Radios worked intermittently. Instructions were fragmented, passed verbally from one group to another, often distorted by panic and noise. Different sections of the mine received different messages, some told to evacuate immediately, others told to stand by. This lack of a single authoritative directive created deadly delays. In emergencies, people do not need information, they need certainty. When certainty disappears, individuals fall back on habit. Some crews attempted to exit using routes they had practiced during drills, only to discover those paths intersected with smoke-filled beltways. Others turned back, searching for alternative exits they had never actually used. The emergency response plan assumed the fire would be stationary. It was not designed for a moving ignition source embedded in the mine's transport system. Fire suppression teams focused on known equipment zones, unaware that the conveyor belt was feeding the fire beyond their reach. By the time the true scale of the spread became clear, those teams were already cut off. Leadership decisions were made with incomplete information. Supervisors had to choose between ordering immediate evacuation through uncertain routes or waiting for confirmation that alternative paths were safe. In several cases, hesitation was interpreted as caution. In reality, it was paralysis caused by conflicting signals. As smoke density increased, physical limitations took over. Visibility dropped to near zero. Breathing became painful. Even miners who knew the layout of the mine struggled to orient themselves. Emergency lighting systems failed in some areas, leaving people to navigate by memory in an environment that no longer matched their mental map. This is where training collided with reality. Drills are clean. They assume clear communication, known hazards, and functioning systems. Real disasters remove all three at once. Under stress, people revert to the most familiar routes, even when those routes are no longer safe. In this mine, familiarity became a trap. Rescue coordination from the surface faced its own challenges. Information coming up from underground was delayed, incomplete, and sometimes contradictory. Command teams could not accurately determine where groups of miners were located or which routes remained passable. Every decision was made under the pressure of time and uncertainty, with lives already being lost below. By the time a full evacuation order was clearly communicated, large sections of the mine were already inaccessible. The conveyor belt fire had fragmented the underground environment into isolated pockets, each with its own rapidly deteriorating conditions. Some miners were moving toward safety. Others were unknowingly moving deeper into danger. This is the cruel truth of complex emergencies. Response systems are often designed for the disaster people expect, not the one that actually happens. When reality deviates from the plan, even well-trained teams can find themselves improvising in an environment that allows no margin for error. If you've ever participated in safety drills and wondered how different things would feel in a real emergency, this is the gap they rarely prepare you for. In your view, what matters more in moments like this, strict procedures or adaptive decision-making? For the miners who were still underground when the fire took full control of the conveyor system, time stopped behaving normally. Minutes stretched into confusion. Directions lost meaning. Environment that had been familiar for years turned hostile in ways training could not fully prepare them for. Smoke did not roll in like a wave. It crept, it slid along ceilings and hugged the floor, filling lungs before eyes fully registered what was happening. Carbon monoxide did its work silently, dulling judgment, slowing reactions, making people feel tired rather than afraid. Some miners reported feeling strangely calm at first, unaware that their bodies were already being starved of oxygen. Groups split as visibility dropped. In clear conditions, teams moved together. In darkness and smoke, people instinctively separate, each trying to find the path they believe is safest. Voices became muffled, shouting wasted breath. Radio batteries drained faster as transmission power increased to punch through interference. Then the radios went quiet. Several miners attempted to follow secondary escape routes they had rarely used. Those routes existed on maps and in training manuals, but memory is unreliable under stress. Intersections looked different in the dark. landmarks disappeared behind smoke. In some cases, people unknowingly walked in circles, retracing the same sections of tunnel while oxygen levels continued to fall. Heat added another layer of confusion. In some areas, temperatures rose sharply as fire advanced along the conveyor path. In others, the air felt deceptively cooler due to ventilation changes, drawing people toward zones that were actually filling with toxic gases. The mine no longer followed predictable patterns. Rescue breathing apparatus, where available, bought some miners precious minutes. But not everyone had immediate access. Some units malfunctioned. Others were shared between co-workers, reducing their effectiveness. Decisions had to be made in seconds. Move now or wait. Push forward or turn back. Help a fallen colleague or keep moving to survive. There were no right answers. Investigators later found evidence of groups stopping in place, likely overcome by smoke, before they realized how severe the exposure had become. In confined environments, loss of consciousness can occur rapidly and without warning. There are no dramatic final moments, no last-second escapes. People simply sit down, thinking they need to rest. This is the hardest part to confront. The mine did not collapse on them. The fire did not chase them with visible flames. Instead, the environment quietly removed their ability to act. By the time many understood they were in mortal danger, their bodies could no longer respond. Some miners came within meters of safety before collapsing. Others were found in areas that, under normal conditions, would have been straightforward exit routes. The difference between survival and death was often measured in seconds, and decisions made with incomplete information. For families above ground, time behaved differently. Hours passed with no news. Lists were updated, then revised. Hope rose and fell with each fragment of information coming from rescue teams. The scale of the loss was not immediately clear. It revealed itself gradually, name by name. The number 121 would later be repeated in reports, headlines, and memorials. But underground, it was not a number. It was co-workers who had shared shifts, meals, jokes, and routines. People who expected to surface at the end of the day. What makes this phase of the disaster so devastating is how impersonal the cause feels to those who lived through it. There was no villain they could see, no single moment they could point to and say, "That's when it all went wrong." The trap was set long before, by systems, habits, and assumptions that felt harmless at the time. If you imagine yourself in that environment, what do you think would have been the hardest decision to make, stopping to help someone else, or pushing forward alone? Take a moment to reflect on that before we move on. When the fire was finally extinguished and rescue teams were able to move safely through the mine, the focus shifted from survival to explanation. What happened here was too large, too deadly, to be dismissed as bad luck. Investigators needed answers, and the deeper they looked, the more uncomfortable the truth became. The official investigation began with familiar assumptions. Gas concentrations were analyzed, electrical systems were examined, structural integrity was reviewed. For days, attention stayed on the hazards mines are traditionally feared for, but none of those explained how the fire had spread so quickly, or why so many escape routes had become unusable almost at once. It wasn't until investigators traced burn patterns along the tunnels that a clear path emerged. Char marks followed the conveyor route with disturbing precision. Areas far from the initial ignition showed evidence of heat and smoke exposure before nearby equipment was affected. The fire hadn't jumped randomly. It had traveled deliberately, carried by the very system meant to move material efficiently through the mine. When the conveyor belt became the central focus, everything else began to align. The point of ignition was traced to a section with abnormal wear and heat damage. Rollers showed signs of prolonged friction. Dust accumulation levels far exceeded what visual inspections had suggested. Laboratory analysis confirmed that the dust composition, combined with sustained heat, created ideal conditions for smoldering ignition. Inspection records were pulled. Maintenance logs were reviewed, line by line. On paper, the belt had passed every required check. No critical issues were documented. No shutdowns were recommended. That contradiction forced investigators to look beyond individual mistakes and toward systemic failure. What they found was a pattern of assumptions embedded in procedure. Conveyor systems were categorized as secondary hazards. Inspections prioritized visibility and continuity rather than physical verification. Risk Assessments had not been updated to reflect increased production loads or system modifications over time. The belt had changed, but the perception of its risk had not. Responsibility, when it came, was diffuse. No single worker had ignored a clear warning. No supervisor had deliberately cut corners. Decisions that contributed to the disaster were made incrementally, often with reasonable justification in the moment, and that made accountability uncomfortable. Regulatory bodies issued findings, pointing to inadequate inspection depth, insufficient monitoring of friction and heat at conveyor components, and a failure to recognize the belt as a primary fire risk. Companies involved responded with revised protocols, new training modules, and updated documentation. On the surface, the system appeared to correct itself, but survivors and families were left with a harder question. Why did it take 121 deaths for something so ordinary to be taken seriously? The conveyor belt was not defective. By design, it failed because it was misunderstood. It existed in a gray zone between machinery and infrastructure, dangerous enough to kill, but familiar enough to be ignored. The investigation did not reveal a mystery, it revealed a mindset. In the end, the reports were filed, the findings published, and the mine became a case study. But case studies don't bring people back. They only offer the chance to recognize patterns before they repeat. And this is where the story becomes larger than a single mine, because the same assumptions uncovered here exist across heavy industry worldwide, quietly waiting for the next moment when routine turns lethal. What this disaster ultimately exposed was not an isolated failure, but a repeating industrial pattern that spans decades, countries, and sectors. The names change, the locations change, the equipment looks different, but the logic behind the catastrophe remains almost identical. A system labeled as routine slowly drifts outside safe boundaries, not through recklessness, but through familiarity. Across heavy industry, some of the deadliest events begin in places considered unremarkable. Conveyor belts, ventilation ducts, cable trays, lubrication systems, insulation layers. These elements are rarely the focus of dramatic safety briefings, because they do not explode on contact or collapse without warning. They fail quietly. And quiet failures are the hardest to justify interrupting production for. After this mine fire, similar incidents were re-examined with new eyes. In multiple cases, investigators found the same sequence: incremental load increases, aging components, dust accumulation, inspections focused on visibility rather than verification, and a shared belief that if it's still running, it's still safe. In some facilities, conveyor belts had been modified beyond original design limits without a corresponding reassessment of fire risk. In others, sensors existed but were calibrated to average conditions, not dangerous spikes. What makes this pattern so persistent is that it hides inside success. Systems that run continuously for years build trust. That trust turns into assumption. Assumption turns into policy. And policy becomes blind to change. When production targets rise, safety margins shrink silently. When nothing bad happens, the absence of consequence reinforces the behavior. The industry often responds to disasters with technology: more sensors, better alarms, automated shutdowns. These tools matter, but they don't address the deeper issue uncovered here. The real failure occurs long before ignition, in how risk is perceived and prioritized. If a system is culturally defined as background, no amount of hardware will fully compensate for human complacency. Another uncomfortable truth emerges when comparing this case to others. The warning signs were not unique. Dust buildup, heat anomalies, minor mechanical irregularities, and informal workarounds appear in incident reports again and again. They are rarely treated as urgent until they align in the worst possible way. By then, investigation replaces prevention. This pattern also explains why lessons learned often fail to spread. Each disaster is treated as a special case, tied to specific circumstances. But when you strip away the details, the structure remains the same. A neglected system becomes critical, a slow failure becomes fast, and response systems designed for expected hazards are overwhelmed by an unexpected one. In the years following this fire, many operations updated conveyor inspection protocols, revised risk classifications, and expanded fire detection coverage. On paper, progress was made, but paper was never the problem. The problem was believing that normal operation meant safe operation. The most dangerous sentence in industrial environments is not "we don't know," It's "we've always done it this way." That sentence appears in almost every investigation, often buried beneath technical language and procedural analysis. It signals a moment when curiosity stopped, when questioning felt unnecessary. This is why the story of this conveyor belt matters beyond the mine, where 121 people died. It forces a confrontation with how danger actually enters complex systems, not through dramatic mistakes, but through quiet acceptance, not through ignorance, but through experience misapplied. As long as industries continue to separate critical systems from routine ones without revisiting that distinction, the conditions for repetition remain. The next disaster may not involve a conveyor belt. It might involve a pipe, a valve, a cable, or a sensor no one has questioned in years, but the logic will be the same. And the question that lingers is not whether another system will be ignored, but which one is being ignored right now. If you stayed until the end of this story, it means you understand how dangerous normal can be inside industrial environments. Take a moment now to leave a comment and write, "Never ignore the routine," so others know you reached the end and truly absorbed this lesson. If this investigation changed the way you look at industrial safety, make sure to like the video and subscribe to the channel for more deep, real stories about disasters that should never have happened. And don't stop here, watch the next video appearing on your screen now to uncover another hidden failure that turned routine into tragedy.